Thank you to all of our esteemed attendees, ladies, gentlemen, students, my friends, and of course, last but not least, our worthy speaker, Dr. Dominic Klyve. Um, as the current chair of the Mathematical Computing and Statistical Sciences Division, it is my privilege and honor to have do a brief introduction of our esteemed distinguished scholar, Dr. Dominic Klyve. I have known him personally for at least 1 decade or so, and I could tell you that the bio that he has submitted is very, very brief. He has so many contributions. The better you search his name on web and find out about him. So Dr. Klyve is a professor of mathematics at Central Washington University. He is author of more than 70 papers in number theory, the history of mathematics, and science, and along with that, applied statistics as well. Dr. Klyve's interdisciplinary work has appeared in journals ranging from uh, gastrointestinal endoscopy to Shakespeare Quarterly. So you can see a diversity of his knowledge and interest and service. Dr. Klyve has won the Alder Award for teaching and the Lester Ford Award for expository writing from the Mathematical Association of America, which is the largest society of professional mathematicians in the entire world, and a faculty mentoring award from our own Council on Undergraduate Research. Dr. Klyve has been editor of the Mathematical Association of America's College Mathematics Journal. And what else? Dr. Klyve has been our leader as well in the Council on Undergraduate Research. He is a past chair of the council that Mathematical Computing and Statistical Sciences Division. At that time, we used to call it Mathematical and Computer Science Division. So in sum, he is a nationally and internationally known distinguished scholars on so much to his credit. It would take me a lot of time to mention more of his contributions. So let's give the floor to Dr. Klyve so that he could do his presentation.
Thank you, Haseeb. That's very generous of you. Good to see you again. And it's true indeed. I was chair of the then Math Computer Science Division, and before that, a counselor. I started working with Kerr fairly early in my professional career. And although I'm not currently serving as a counselor, it still holds a dear place in my heart. So it's wonderful to have a chance to come back and see you. And I see some old friends and names that I know on the list. So hi again, people I've not talked to for years. I when Haseeb asked me to give a talk, it's a little bit open-ended. How do we talk about undergraduate research to a group of people who spend a lot of their time thinking about undergraduate research? Some sense, well, I love telling stories. I wonder if I have much to say that's new. And some of this will be things a lot of you have thought about already, and that's of course fine. But one thing I've been struck by, and one thing that I don't remember talking about with people very much during my time there, is thinking about students not just as people who were mentoring through undergraduate research, people who were helping, but also people who help us. And so this is my main focus today. To faculty members, I will encourage us all to think about the expertise of our students, the life experience of our students, and what they can help provide for us. Similarly, for the students who are here, I'll encourage you to think about things that you do well, things that you have expertise in and background with, and how you can bring that into a professional environment in ways that might always be slightly different than we think about in the classroom. So listen, let's start with the introduction. You know that first paragraph of every paper that you read that doesn't really say anything? This is my slide that does that. Undergraduate research is good. Yes, we know that, but let's state it out loud here. And it does a lot of things for us. When you do undergraduate research, you get to work with others in a way that's fundamentally different than the classroom. But you learn in a really deep and in-depth way is, again, probably different than what we get in a certain class. When we engage in undergraduate research and all research, you have a chance to write and to present, which is a marvelous opportunity for us to grow. It's good for us professionally. Students who do undergraduate research will just look that much better when being assessed by an employer, by a graduate school. And then you get to meet people. And once you love a field enough to want to do research in it, meeting people who also like doing it is great. But when we think about this, what do we say? And when we describe doing undergraduate research, it's often sort of put in this language where experts in the field, and experts here are faculty members, they have a chance to pass on knowledge to students, to pass on disciplinary expertise to students, to pass on techniques and ways of moving, ways of doing and knowing to students. And that's true. It's fundamentally, not deniable that faculty have more experience in whatever field we're working with than the students. But one thing that I think is really amazing is faculty get big benefits when they work with students. First of all, it's fun. Students are interesting and exciting people in lots of ways. Maybe if there are students, we get more research done. Maybe there are some benefits to us, but I think sometimes when we talk about benefits to faculty, these feel a little bit more fuzzy. The benefits to students are really easy to document, and the ones to faculty are kind of along the lines of it's fun and interesting. But one thing that's become really clear to me over the years is that the students also have a lot of expertise. Our students do things that are surprising and audacious and creative, and the students I work with come from very different places than I come from, which means they have life experience to draw on. They have other expertise to draw on. They have knowledge that they can bring to bear that wouldn't be my approach. And this can be really beneficial in ways that we can make really concrete. And I want to stop trying to convince you of this in general and tell some stories. And this is a math-friendly group, so I'm going to tell mostly math stories. These won't all be math stories, but I know I can tell them here. So I'm going to tell you one of my favorite games. And students, if you're bored in some class later today, not a math class, but some other class, and you want something to do, consider this game. It's a good one. Here's how you play. Think of a number. Next, write down all of its factors. And I'll tell you what I mean here is its proper factors. The factors of a number for this particular example will not include the number itself. Now, add them up and see what you notice. Let's make this a very fuzzy game. See if we see anything that happens. So if I want to add up the proper factors of n, I'm going to refer to this as S of n to make my notation easier. And so just to make sure we're on the same page, if I want the sum of the factors of 8, well, 8 is a power of 2, so it's only divisible by other powers of 2. It's divisible by 1, 2, and 4. And if I add those up, I get 7. How about 12? Before I go on to 12, let's note if I add up the factors of 8, I get less than 8, right? 1 plus 2 plus 4 is 7. Well, the factors of 12 are 1, 2, 3, 4, and 6. If I add those up, I get more than 12. Okay, I don't know yet if this is interesting, but it might be, and we can try this out. And let's ask an open-ended question. Open-ended questions are great for research. They're really great for student research. Because if you ask a very focused question, it might be hard to answer. If you ask a really broad question, there might be some version of it you can't answer, and that could be interesting. So here's my broad question. Is there a relationship between S of n and n? Now, several years ago, I had 2 summer students. Their names were both Nicole, and we decided we would look into this. So the question is, if you sort of explore this difference, explore these numbers and relationships, once you start thinking about it, you might ask this natural question. Which numbers can you write as a difference of S of n and n? Now, I just found out that for 12, S of 12 is 16, and 16 minus 12 is 4. So for sure, 4 could be the difference. I know 1 or maybe -1 could be the difference if I have 8. How about 2? Is there any number for which S of n minus n is equal to 2? And the answer is yes, 20 works for that. You sum up the factors of 20, you'll get 22. How about 3? Is the difference ever equal to 3? And that's pretty easy. 18 works for that one. 6. Is the difference ever 6? And we're just sort of trying random examples here. You can get a difference of 6, but it turns out this is a lot harder to find. You can work with paper and pencil for a long time and maybe believe it's not possible, because the first integer for which this difference is 6 is 8,925. All right, 2, 3, and 6. How about 1? Is there any number n for which I can add up the factors of n and get 1 more than n? And it turns out this is not known to mathematics. So here's a pretty basic question. I could play this game with 3rd and 4th graders as long as they know how to divide. It's pretty easy to write out factors and subtract. Is there ever a number equal to 1? And it turns out, again, we don't know. This is beyond the reach of what number theory can do today. And first of all, I love this. This is always one of my favorite things about number theory, is that we can ask questions that elementary students can answer that no professional mathematician can, but also suggest there might be something interesting here. And what we ended up doing, and I think I'm not going to, what we ended up doing is trying to make a list of numbers that seem never to appear here. Nicole were very junior students. They didn't have a lot of experience writing proofs, and so we did a lot of generating of examples. We learned to write efficient computer code. We found a very clever method that let us speed up our code dramatically by skipping a lot of examples. We were able to search literally quadrillions of numbers and able to find a lot of these that don't appear. There are several numbers that seem never to appear on this list. No one seems to know why. This just came from them asking a good question. Let's ask a very similar question. Let's think of a number. We'll play the same game we did before and add up the proper factors of n to get s of n. Now, first we'll check whether that sum is bigger than the number itself. Right? If you add up the proper factors of the number, do you get something bigger than what you started with? If you do, let's try removing some of those factors to make the rest add up to exactly n. So let me see if I can make this clear with an example. If n was 12, remember, if we add up the factors, we have 1 plus 2 plus 3 plus 4 plus 6 to get 16. Is there a way I can take a subset of those factors, add them up, and get exactly 12? Well, you probably see it. It's not particularly difficult to recognize if you remove the number 4 and you add it up, we'll get exactly 16. Here's a slightly trickier one. How about 42? The sum of the factors of 42 is 54. Again, is there a subset of those that add up to exactly 42? Or put another way, can I remove some of those factors that add up to exactly 12? Well, you look at it for a minute and you might say, oh yeah, 1 plus 2 plus 3 plus 6 equals 12. So if I take those off the list, the sum will get 12 smaller. I can get exactly 42. And indeed, I'll tell you, this usually happens. Usually, if you add up the numbers and get more than what you started with, for the nerds among you who like words, those numbers are called abundant numbers. An abundant number has a property that if you add up its factors, you get more than the number itself. Usually, if you have an abundant number, you can pull off some of the factors and get exactly the original. Weirdly, sometimes it's hard to find this. Let's take 70, add up the factors of 70, and you get 74. So I'll ask this for the third time. Is there a subset of these numbers that add up to exactly 70? Well, to find that, we'd have to find some of those factors on the left that add up to 4. And pretty clearly, there aren't any. This is not going to be possible. The 70 is an abundant number that doesn't behave this way. It turns out in the literature, this number is called a weird number. Weird numbers have this property. They're abundant, but no proper subset of the factors add up to the number itself. Now, I was teaching a once a week honor seminar some years back, and a student named Luke who discovered weird numbers. The basic thing activity for that week. So everybody had to look up some kind of number in the encyclopedia of integer sequences and give a short presentation on what the numbers were. And Luke said, I'm kind of weird. I wonder if there are any numbers called weird. And he found these and started presenting on them. And in the presentation, he showed us the largest known weird number, which at the time was this. This number is abundant, but no sum of its factors add up to the number itself. And I looked at that and I thought, that's not a very big number. I mean, it's a big number if you're counting things, but in terms of sort of what we can handle numerically, we might be able to sort of find a way to get past that. So I asked the students if they thought we could get a bigger one, if we could set a record for the biggest weird number, and they were way on board. So our seminar shifted immediately from whatever we were doing to weird number searching. We sort of, threw out the syllabus and picked this up, and they ended up meeting extra sessions, and they would come in early to work on this, and we put code together and then better code for it. And after a few weeks, in fact, we not only beat the record, but smashed it. After a few weeks of this extra work, turns out this markedly larger number is also a weird number. At the time was the largest one. I'm pretty sure it's still the largest weird number, but I've not looked in a year, and it didn't occur to me till this moment. I probably should have looked before this talk, so maybe somebody broke the record a few months ago. But I think this is it. And it's a wonderful thing that because they were so excited about it, because the students were audacious enough to think this could be done, we decided to try. And the trying is really what made it possible. So students don't only ask good questions and have great motivation, they also cross disciplinary boundaries, sometimes in ways better than their faculty can. So I usually teach math classes, but I also have the privilege of teaching in the Douglas Honors College on campus. Our Honors College has an interdisciplinary curriculum where students can meet things like gen ed requirements in interdisciplinary seminars, explore knowledge in, I guess, less traditional ways. One of my students was Kate, who actually had come here from theater school. She had devoted herself to being a professional actor, had studied theater for a while, and decided it wasn't going to be for her, that she really wanted to go into law, so she came back to college to get a bachelor's degree before heading off to law school. And she was interested in Shakespeare, but she had this other interest, which might not have occurred to me easily. She was interested in studying the people who study Shakespeare. So we might ask questions like, maybe you're familiar with this literature and maybe not, but you probably are not surprised to know there are professional Shakespeareans who spend their lives studying Shakespeare. Some of them write papers and books about particular plays of Shakespeare. And so we could ask questions like, do the plays that people study, are those choices influenced by what's happening in culture? Maybe the Roman plays are more popular when our country is at war. Maybe Taming of the Shrew is more popular in the height of the feminist movement. Maybe we can find some patterns here. And because Shakespeare people are nerds like math people, they have done a really nice job organizing all of their literature. There's sort of a Shakespeare version of Math Synapse. You can go online and you can find all the papers and dissertations and books and articles that have been written about Shakespeare, and they're subcategorized by what they're about. So Kate went online and started counting. And the final count was simultaneously fascinating and boring. It looked something like this. This is a list of different plays of Shakespeare, various years in the last half century, and then the number of works about that play published in that year. So in 2005, there were 22 papers about Cymbeline. In 1963, there were 74 papers about Hamlet. Weirdly, in 1964, the number of papers about Hamlet skyrocketed before going down in 1965. Well, that one's only weird for a couple seconds until you realize that 1964 was Shakespeare's 400th birthday. So in fact, there are more papers about everybody that year. There were lots of extra journals and books that were published. So we have this list. Another question is, what patterns can we find? It's a simple data set, but exploring simple data sets is fun. Kate wasn't an advanced statistics student. She had some basic skills, and so we started doing some basic investigation. We started doing things like she counted in total how many plays were there and how many papers were there about each play. And it turns out if you make a plot of the number of papers about each play, it comes pretty close to this beautiful geometric distribution. You move on down the list, it decreases exponentially the number of publications about each one, except for one, which is Hamlet. Hamlet is way more popular than it has any right to be. She counted up various breakdowns by category of play, found plays that have increased or decreased more in relative popularity. So this is the plot not of the number of publications about each play, but if you look at all the publications in that year, what percent were about this play. This tells you that back in 1960, 4% of all people writing about Shakespeare were writing about Julius Caesar, and also about 4% were writing about the Tempest. By the 21st century, it had branched out dramatically. Tempest was 3 times more popular, and so we're seeing that to a scholarly audience. Julius Caesar is less cool, perhaps, than it used to be. The Tempest is greater. So we were exploring this. It was really fun and interesting. I was really curious whether we could do something with it. And so I wrote to the editor of a couple different Shakespeare journals and just said, like, listen, would you ever be interested in this work? And I'm thinking maybe not, because they don't publish about Shakespeare scholarship. They publish about Shakespeare. And this is almost about Shakespeare, but not quite. Right? Remember where we started? This is about people who are studying Shakespeare. But a few of them wrote back and said, yes, I think we might really be interested. And the editor of Shakespeare Quarterly wrote back and he said, yeah, this is great, but listen, you absolutely need a Shakespeare co-author. You told me, for example, you discovered that the play King Lear was really popular in the 1980s. He said, well, everybody knows that. At least if you're a Shakespeare person, everybody knows that. It turns out early in the 80s, they discovered various alternate versions of the text, and the world got really excited about them and explored them for a while. So if you tell us you've discovered this, no one's going to care. Plus, the way you're describing things doesn't quite make sense to us. You want to talk about this differently. So he suggested a co-author to me, a woman named Laura Estel, who was the editor of the World Shakespeare Bibliography Online. I contacted her. She agreed to collaborate with us. And so the three of us worked together and put this paper together, a paper of analysis of writing about Shakespeare, which was a marvelous experience for me. I got to work with this woman who was literally a Shakespearean, and something I never would have done without a student there to be bold enough to ask about the idea and to push it forward. So grateful to Kate for this. Feel really happy for this experience. The other thing, when we started doing this, video conferencing wasn't very popular because the project started a decade ago, really. And so all of my correspondence with Laura was either via email or via margins and comments in Word documents. And this occurred to me recently when we were exchanging emails about something else, that although I feel like I've known her for 10 years, I know the names of her children, I have some idea what she's done with her career. We've never actually spoken. My only communication with her has been email and Word documents. And part of me wants now to call her up, and part of me thinks it's kind of fun never having done so. Not only will students move us beyond disciplines, they literally have expertise in things that we don't have. And so I'm going to tell a story that's a lot farther from mathematics than most of these, but a story that will have a name familiar to probably everybody in this room. See, again, quite a while ago, I was at an awards dinner here at my university, and I met a student named Olivia. Olivia was a brilliant student. She was fluent in Spanish and French, just planning to head to grad school in linguistics. And so I told her I had this sort of back of the mind idea for a project that I was interested in, and I really could use some help with it. See, the idea goes back to Euler. Leonhard Euler is a name that is probably familiar to everybody here. Euler is my favorite mathematician from history. One of my first sort of professional activities on the national level was founding what's called the Euler Archive. Before it was easy, before there was Google Books to search for things, some others and I, Lee Simkowski and I, started this. Took the process of going back to Euler's printed 18th century works, scanning them all to PDF, and putting them online so the world could easily access Euler's original works. It was a fun activity for me. It was a nice experience of sort of being involved in mathematics. It also meant that I spent years engaging deeply with individual documents written by Euler. I spent an enormous amount of time with Euler's primary sources. And at one point I found that in 1780, he wrote a short article that classified vowels across languages. And I think I'm describing, I don't think I put a lot of the background here about the paper. He wrote this in 1980. It wasn't published until 1863. See, Euler was so prolific, the journals at the time couldn't keep up with his work. Basic thing they did toward the end of his life is when other people submitted papers to the journal where he usually published, they would publish those papers. Whatever space they had left, they would just fill with Euler. And there was like an Euler pile in the office. They would dig down as far as they needed for papers, and they would put those in. Euler died in 1783. They kept publishing his papers until 1820. It was 37 years until they published all of his backlog. And that was only because in 1820, they ran an all Euler issue just to finish it. Well, a few more papers were found later. Then in the 1860s, somebody found a giant cache of his works that had never appeared anywhere and published a giant 2-volume work with 60 more papers by Euler that have never been written. It's a remarkable story. One of them was this really odd thing where he classified vowels. And basically, when this work appeared, nobody cared. Nobody cared because it appeared after this technical work on differential equations and before this review of a meteorology book. The only math people and physics people read Euler's works, and they weren't interested in this. And the linguistics people didn't look at this. But I had read this, and I'm like, this is kind of interesting. What does he do when he classifies vowels? Well, he first says some are thicker and some are thinner. So a thick vowel might be like an and a thin vowel might be like an eh. Also, they can be open and closed and middle vowels. And he gave some example of open vowels and closed vowels sort of clip off quickly. They have different locations based on where they're formed in the mouth. There can be anterior and posterior and middle vowels. And most of you are muted, so you can play this game if you want and nobody will know. But try making some vowel sounds and see if you can tell where in the mouth they're made. And whether you've thought about this before or not, you might notice they really do have mouth positions. So maybe we can use this to classify vowels. Well, if we take just these last two categories, open, closed, middle, and anterior, posterior, and middle, this gives us sort of 9 locations in, again, we're a math-friendly audience, in two-dimensional vowel space. We could locate these. And so Euler put this paper together, his Meditatio de Formatione Vocum, his meditation on the formation of the voice, to try to put these together. And he gave specific examples where, and you can tell sort of his language background by the examples he gives. He says the ah in the Hebrew word patach is a thick front vowel, and the ah in Swabian or Bavarian is a thick front middle topped vowel, and the French I is a middle front vowel. I sort of put all this together. So I showed this to my student Olivia, and I said, I think this is super interesting because I think this is really ahead of its time. Let's see if we can make sense of this. So she took all these vowels that Euler sort of described and put them together into a two-dimensional chart. So here we have examples of vowels that are thicker and thinner, examples of vowels that are more front and more back. And we stared at this and said, oh my gosh, this is maybe cooler than we thought because it reminds us of something else. If you've taken a linguistics class, you've been introduced to the International Phonetic Alphabet. If you've ever Googled a different language on Wikipedia, you've seen vowels classified this way. But modern linguists do, and they have since about 1960, put vowels on this IPA vowel chart. IPA here is the International Phonetic Alphabet. And if you were to look up how to pronounce vowels in Dutch, say, and you can do this on Wikipedia now, it'll tell you that the A is here and the O is here. And if you're sufficiently talented, you can look at the location on this chart and know exactly how the vowel sounds. I cannot do that, but linguists can. Also, as a quick personal story, be careful getting good at this. I had a linguist professor who traveled to Spain at one point, and he didn't speak Spanish. But what he did do before he traveled is he looked up how to pronounce the language in the region he was traveling to. And he pulled up one of these charts, and so he figured out exactly how they pronounce consonants and vowels in the particular region he went to, which meant when he tried the few words that he knew in Spanish, he sounded like a local because he had mastered the dialect, but he couldn't speak. So everybody thought he was some sort of idiot who couldn't put basic words together, even though he was clearly from there. So sometimes it's good to have an accent. Anyway, you can classify this. This is what people use today. This is what Euler did. It turns out if you rotate this, you can overlay them and they're almost identical. Which means what? It means 180 years before linguists put together this two-dimensional vowel chart, Euler had done the same thing, which is amazingly cool. And we're like, we have to tell the world about this. So we wrote this up and we put this in a sort of the standard journal on the history of linguistics, which yes is a thing and it's very fun and 100% would not have happened before Olivia. Indeed, when I wrote this paper, I used to have on my wall a list of various research projects I was working on. I had little sticky notes for them and I had places for them. This one was when I started work. This is when I started writing. This is when I was a co-author, as I could keep track of what I was working on. And I had this one on my list for years of started work, and I eventually moved it to abandoned projects. because it was clear to me that although I loved the idea, I would never have enough expertise in the history of linguistics to write the paper, nor would I ever take the time to develop the expertise. It was just much too big of a lift. She had it, she put it over the edge, and I'm simply happy, simply thrilled that we were able to do this. And the thing is, once you start combining what you do with interdisciplinary thinking from students, it's really hard to stop. If you've been at my talks at national meetings, you've maybe seen me mention this guy. This is my second favorite 18th century scholar, if Euler was the first. Georges Leclerc is the Comte de Buffon. He, among other things, is in charge of the big gardens owned by Louis XIV, in charge of his sort of science exhibit. He also wrote this marvelous essay, the Essay on Moral Arithmetic, in which he combines math and philosophy and ways of living in utterly fascinating ways. If you have not read this before, strongly recommend. If your French is rusty, there's 2 English translations. There's one that's been published, and then one that a colleague and I did, because I didn't like the one that was published. I'm fairly certain you can find mine if you search for my name, but I'm not sure about that either. If not, if you want to read this, let me know. I'm happy to send this to you. So I started showing this to students, and because it's so rich and because it crosses boundaries in so many ways, a lot of students had interesting ways to look at this. So Stephanie looked at this moral arithmetic and tried to tease out exactly what that meant. 2 students, John and Rebecca, looked at this and noticed a lot of connections between what Buffon was doing and what we now call the p-value in modern statistics. And indeed, in the years since, building on their work, I've put together a project that teaches p-values to introductory stats students using primary historical sources. I've spent several years in the last decade working on a project to build primary historical source projects to teach mathematics, and one of them is a p-value. It came directly out of this work. Anna looked at this, had something Buffon wrote about experiment and certainty, and found an early fractal. See, there's this game that Buffon played. It's a fun game. It goes like this: throw a coin in the air. If it comes up heads, I'll give you $1. If it comes up tails, flip it again. If it comes up heads on the second time, then I'll give you $2. If it comes up head on the third time, I'll give you $4. If it comes up heads on the nth time, I'll give you 2 to the n minus $1. But every time you flip tails again, you double the money you're going to win. So keep flipping until you get a heads. We'll count how many tails you had. That'll control how much money I'll pay you. Now the question is, how much should I pay you to play this game? Well, let's think about this mathematically. We've got a minute to work through this. If you get heads right away, there's a 50% chance. 50% chance you get heads right away. If you do, you'll win $1. So it's expected value of 50 cents. I'm going to see if I can. If you don't get heads for the second time, there's a 1/4 chance of that. But if you do it, you get $2. That's another 50 cents. You add this up and think about it for a minute. It turns out the expected value of doing this is infinite. Now, at the time, this was a problem for probability theory. Probability theory was new. They had thought they'd understood expected value calculations. They worked this out and found the expected value was infinite and said, what does that mean? Is that even possible? Buffon said, this is a problem with how we think about probability. After all, even though the expected value is infinite, nobody would pay $10,000 to play this game. So maybe we're doing something wrong. Well, I was teaching this to a history of math class, and Anna said, what happened? And she read ahead and saw that Buffon decided to actually try this out. Buffon said, I'm going to play this game myself 2,048 times, and I'm going to figure out what my average winnings are. So he played, he flipped, he actually hired a kid to help him, it says, in the original source. And at the end, he found that he had an average winnings of $10.48. So there, he said, the expected value is not actually infinite. It's a little over $10. Anna said, would we always get a little over $10? Can we try this again? Now, it's pretty easy to write code to simulate flipping a coin. And so we threw together a program, ran it several times, and found out that we got really different answers every time. This seemed interesting, so we explored a little further. We actually did this thousands and thousands of times. I think we ended up doing this 1 million times. And then, so each time what we did was play the game 2,048 times, write down our average winnings. Now play the game 2,048 times, write down our average winnings. And now we can plot a histogram of the average winnings And that histogram is the picture I'm showing you now. This bizarre, almost fractal life-like distribution, right? It's not remotely normal. It doesn't look like any shape we've seen before. We get this utterly bizarre behavior. And it happens when you look at something unusual and ask a question from a different lens. So Anna and I thought this was so interesting that we wrote this up and got this published in the College Math Journal. This was before I was involved with the journal, but a marvelous chance for a student to be involved in doing this. So listen, it's true. Faculty are experts and we can treat ourselves as experts, but every time I work with students, I'm reminded they also are brilliant. They're also expert in their own domains. They're creative in wild ways that would often not occur to me. And I'm utterly convinced our work is more successful and my work is more successful because of my work with students.